Okay, thank you, and good day to everyone. My topic for today is what's new in WDSP, and I've picked some particular things that I'm going to talk about. But first, for those who might not be aware, let's see, this is not changing slides. No, I don't know, it's flashing.
It's flashing. It's running out of battery.
It's running out of battery?
I don't know.
No, it works.
No? That works.
Works. This is for green for the
Yeah.
pointer, and this is for forward and backward.
Okay, let's try forward.
No, this is, you try backward.
Oh.
This is forward. Ah, it works.
Okay. I thought forward might be up, but no, it's down. So, first of all, for those who might not know, what is WDSP? And WDSP is an open source signal processing library written for the Open HPSDR program, primarily by me, and it contains the basic algorithms that you would expect in a DSP library, plus a lot of advanced algorithms, things like our adaptive pre-distortion, our spectral noise reduction, spectral noise blanking, and the topics that I'm going to cover today, which are low latency for filtering, advanced speech processing for transmit, basically to replace those racks of audio equipment that some of our audio files use, a second version of adaptive pre-distortion, and also adaptive resampling. So I have a lot to cover. Let's jump right in on FUR filtering. There are three common latency problems with FUR filters, and the first one is that most SDRs use linear phase FUR filters, which happen to have a lengthy delay related to the number of coefficients in the filter. Secondly, we like sharp filters, and to get sharper filters, we have to use more taps, and so we have even more delay to get sharp filters. And then the third problem, for sharp filters, we have a lot of taps by now, and at this point, they're very inefficient to process in the time domain. So we need to go to the frequency domain using FFTs. But the FFT is inherently a batch process. We have to collect a bunch of samples before we can do the FFT. And so we have to wait to collect those samples, and that adds additional latency. So three problems. Now, let's go back and examine linear phase. There seems to be this belief that linear phase is required for example, our bandpass filters. It's absolutely not true. There's another class of filters called minimum phase filters, which have a much lower latency. Perhaps the reason that linear phase filters became so popular is because they're easy to design. There's easy algorithms, guaranteed to converge, don't require much computing performance. But with linear phase, with minimum phase, we now have faster computers, and we can be a little smarter about the algorithms that we select so that they are also guaranteed to converge. And and we can do things like double buffering if needed, where we use one filter while we compute the next filter, if we are, for example, adjusting the width of the passband in real time. The minimum phase works perfectly for almost all modes. One thing it doesn't work well for is if you're receiving AM and you are off frequency. However, in that case, why not just use linear phase? Now, I'm going to jump straight to some results here. What I've shown is a chart of latency, and here we have filter shape factor. So sharp filters are on this side, sort of sloppy filters are on this side. And the red is minimum phase filters, showing the latency. The blue is linear phase. This is antenna to speaker, system performance measured on our Open HPSDR Power SDR. You can see there's quite a significant difference. One thing you'll note is that for minimum phase, there's significantly lower latency. The second thing you'll note is that for minimum phase, the latency is virtually independent of how sharp you make the filter. You could have extremely sharp filters and still low latency. Now, something else though that I kind of snuck in here is that the DSP buffer size is 64 for all of the points on this curve. That means the number of taps must somehow be independent of the DSP buffer size in this system that we have in WDSP. So we haven't had to increase the buffer size to buffer more samples to do larger FFTs. Somehow there's some magic there. So let's explore that. To understand it, let's go back to the way we implement a FUR filter in the time domain. And it's done like this. We put in one sample at a time into a buffer. We have a pre-computed impulse response. We multiply sample by sample, add up all the results, we get one output sample. Now you can see that's very inefficient because to get a single output sample, we have to do a lot of multiplies and a lot of adds. So there are ways around that, as I mentioned, using FFTs. The overlap save method is one of the ways around that. I'm not going to explain this in detail. You can find links on the internet if you're not familiar with it. But a difference here to observe is that in this case, we collect all of those samples in an entire buffer in advance. That's what adds the latency. We process it, and then we get an entire output buffer of samples. So we can replace the first picture with this second picture. Now, let me explain the magic. How do we keep the buffer small even when the filter gets long? And to do that, let's go back to the time domain representation. I'm going to perform two transformations on this diagram. Here's the first one. I'm going to pull those registers apart. This is mathematically equivalent to what you saw on the previous slide. We just broken the addition, we've broken the addition down into two levels, one level here and one level here, but we're still adding everything up. Now, we also observe that each of these is a small time domain convolution. We know we can replace a time domain convolution with an overlap save unit. So this is the second transformation. Okay? Now, each of these overlap save units, however, is much smaller. The buffers in those are much smaller, and we have to collect far fewer samples before we can run the process. So we can put in a small buffer and get out a small buffer and just add more overlap save units to lengthen the filter. So that's the way it works. I have to move on. Advanced speech processing. Why do we want it? Well, we want to have more punch in our audio. We want to be louder. We want to sound better. And overall, we want to have more fun and communicate more effectively. Before I explain the new tools that we've added in the last couple years, let me tell you a little bit about the audio pipeline that we had before that. And it was a fairly complete pipeline for an SDR. We began with a noise gate with nice raised cosine gain transitions, had a continuous frequency equalizer where you can specify a number of frequency points, specify the gain you want at each point, and the gain will be interpolated in between those points. We have a non-distorting leveler, a speech processor that behaves like an RF speech clipper, controlled envelope single sideband, which was introduced by Dave Hirschberger, W9GR, back in 2014, and a non-distorting ALC. That was the previous pipeline. Now, the more recent additions have been a phase rotator, a new continuous frequency compressor, and along with that, a second continuous frequency equalizer. We'll examine each one of these. I might just mention at this point, the continuous frequency compressor and equalizer work much like the other one. We specify frequency points. In this case, the compression is interpolated between the points at which you specify it, as is the equalizer gain. So, how do we do this? Well, or maybe why first. Let's look at the phase rotator. Why do we want this? We want the phase rotator because we have a fixed modulation range. It's fixed by the DAC in an SDR. We can only drive it so hard. You can't go beyond the maximum value that you can feed it. And in FM, we're limited by some deviation that we don't want to exceed. But we want to maximize our modulation. We want to use the entire dynamic range that's available. And the phase rotator makes the voice waveform more symmetrical so that we can take advantage of that full range. Let's look at it in a bit more detail. First of all, I'll mention that this is not a new concept. Back in 1959, Leonard Kahn patented a circuit like this, a lattice LC network, all-pass filters. He marketed a product called the Symmetripeak into the broadcast industry for this purpose. And then in 1999, Gary W3AM published an op-amp circuit of all-pass filters, which perhaps made this a bit more popular in the amateur radio community. Obviously, what we're talking about here is doing this kind of thing in software in WDSP. Here's an asymmetrical speech waveform. This is a fairly typical thing that you'll find. And while the average value of this waveform is 0, we see the positive peaks going to 1, while the negative peaks are only going down to about minus 0.5. Now, if we run this through a phase rotator, we can get this. And here we've made that waveform more symmetrical without changing its frequency response. We have all the same frequency components at the same amplitudes. We've just shifted them relative to each other in phase. What is the effect of this? Well, in this example, if we look at what single sideband power it will generate, you can see the red waveform has a lot more high peaks, and in fact, when you calculate it, there's about a 64% increase in average power in this particular example. Okay, moving on to the continuous frequency compressor and the continuous frequency equalizer. These are done together in the frequency domain, which means that we're going to do an FFT, do the compression and equalization gain, and do an inverse FFT. Well, that looks simple, right? It turns out it's not quite this simple, as things in digital signal processing often are not. And the problem is that we can't just do an FFT and then individually modify the frequency bands and do an inverse FFT and get a result that does not have some significant artifacts and distortion. Okay? If we weren't modifying the frequency bends individually, then we could, but we could do an FFT and inverse FFT. But you can't do the FFT, do individual modification of frequency bends differently, and do an inverse FFT and get a result without problems. So we have to solve that problem. And the way we do it is something called the weighted overlap add method, where we apply a window function to overlapping sets of samples. Then we do our processing. And by the way, this was the new input for the latest windowed set of samples. We do our processing, and then we come over here, we window again the output samples, and we add together those that line up in time. So we had an input buffer this size, we had an output buffer this size, we had to do some overlap to get those, and we just keep going, okay? So that's the way we avoid the problem. These tools, by the way, have been reported to work very well, and we have a number of folks that are using these tools as opposed to some racks of audio equipment that they'd invested quite a bit of money in. Okay, Pure Signal 2.0. The goals for this release were to especially deal with overdriven and poorly behaved amplifiers. Not that anybody in the ham community would ever overdrive an amplifier. To improve the user interface, which is not really part of the DSP library, but I'll talk about some things. And also to install some basic capabilities for future developments we may want to do in Pure Signal. This is a well-behaved amplifier. This is the Amp View display, a utility that's included with the software. Here in blue and yellow, you see the software has measured the magnitude and phase response of the amplifier. And in red and green, you see the correction curves that have been calculated and are being applied. This is a poorly behaved and overdriven amplifier. See some rather strange things in the magnitude response, but perhaps more importantly, you note that right up here, we're so much into gain compression that this is completely flat. In fact, in some cases, it even declines, less output as you drive it harder. So that's a problem, because to calculate this, to calculate this correction curve, what we're trying to find is what input value produces each output value. But if this curve is flat at the top, there are many input values that produce the same output value, and the equations can't really be solved. So to get around this problem, Pure Signal 2 uses a priori knowledge of what that correction curve is supposed to look like. It knows what it's supposed to look like, and when there's an inconsistency, when there's something that's indeterminate, it uses its knowledge of what the curve should look like to fill in the missing information. User interface, one of the main things is that now you don't have to open up any auxiliary windows to use Pure Signal. You can simply turn it on, and you get an indication right here on the main console of what's happening. If you're an advanced user, you want to know more about the internals, or there's some problem you're trying to debug, we've also redesigned the auxiliary window. When you first open it, it looks like this. If you click Advanced, you get even more information and controls. And then for the future on Pure Signal, we have added a capability. We may want to work on small memory effects, and so we've added a capability to separate the memoryless behavior of the amplifier from the from memory effects. And so I've showed you an Amp View display. In this case, we have, you can tell by the fuzziness there, we have memory effects plus the memoryless behavior of the amplifier. Over here, we've taken away the memory effects. We have only the memoryless behavior of the amplifier, and the memory effects themselves are the difference of the two curves. Finally, my fourth topic, adaptive resampling. So let me first explain the problem. We have an SDR box. It has a lot of digital hardware. It has a clock that runs that digital hardware. We have a computer. It may have a microphone and speaker attached or be running a digital mode program. Well, it has its own clock. And we want to transfer digital samples back and forth between the two. Now, the problem is, even if we pick a common sample rate like 48 kilohertz, if those two clocks aren't synchronized, we're not going to have exactly 48 kilohertz in each direction. And eventually, in these buffers that we have in between, we're going to have overflows or underflows, too many samples or not enough samples. So the way we solve that is by putting adaptive resamplers in these paths. And the job of these adaptive resamplers is to sense the difference in the ratio of the sample rates. because they're not exactly the same, and to resample those samples as they go through to provide the right output sample rate. Now let's look in a little more detail at those adaptive resamplers. Within each of those, we have a variable resampler, which accepts a ratio. I called it VAR here. It's just the resampling ratio that it operates at. And we have the buffer that we saw earlier, and we have to have some control to calculate VAR. So the way we generate that signal, VAR, is first of all to count the samples coming in to the resampler and count the samples that are being pulled out of the buffer and compute the ratio. That gives us VAR. And you might think that's all there is to it. That's a sufficient calculation. But on average, we want to keep that buffer about half full. So there's another term we need in the feedback, which we derive by looking at how full the buffer is and slightly adjusting the ratio based upon how full the buffer is. Let's look at a little more detail at this interesting part called the variable resampler. Now, its job, we have a bunch of samples. What we want it to do is, mathematically at least, to recreate a continuous waveform and then to sample that continuous waveform at different times than the original samples. So that's its job. And we also want very low spur levels so that we can use this for IQ data as well as audio data. I'm going to explain how that works. And to do that, I'm going to use another DSP block called a polyphase resampler. And this is something you may be familiar with, but I'm going to present it maybe in a little bit different way than you've seen it before. This particular polyphase resampler is an interpolate by 4 resampler. So what we have input samples coming in. Here's the last one. We have created a filter impulse response that looks like this, a bunch of samples of an impulse response. We want to create output samples. The way we create our first output sample is by multiplying each input by one of these impulse response coefficients that lines up with it exactly in time. Then we add all of those up, we get our first output. Now, to get the second output, we shift the impulse response. We have the same input samples, we just shifted the impulse response over by 1. Notice that in both the first case and the second case, the impulse response gets centered on exactly where in time we want the output sample. Okay? And again, we multiply, add, we have our second output. Same thing for a third output. Same thing for a fourth output. Now we're ready for our next input sample, and we just keep shifting the impulse response, keep generating outputs. The problem, well, key points. We always centered the impulse response on the time where we wanted the output, and we multiplied by coefficients lined up exactly in time with the input samples. Problem that we have in the variable resampler is that we have to generate the impulse response before we know the sample rate. And so we still center the impulse response in time where we want the output sample. However, we may not have impulse response samples that line up in time with the inputs. So we have to make those. And in WDSP, we do 2 things. One is we create a much denser impulse response. So at least we're going to have samples that are closer to the times at which we need them. The second is we linearly interpolate between those to get impulse response samples exactly at the times we need them. One final point here. The operating system environment, perhaps especially Windows, is a bit hostile for signal processing. The operating system tends to get distracted and go off and do unknown things, and eventually something isn't going to get scheduled when it should, and you're going to have an underflow or overflow. And so there are graceful ways to handle that we built into WDSP. For an underflow, ramp down the signal gradually, wait a little while till you collect some more samples, ramp it back up. For an overflow, cut out a section of samples, throw it away, and blend along a raised cosine the signals on each end. So that's there also. And that's it. Thank you.
Thanks so much. Questions?
So the observation of the buffer fillage, right? That happens at the audio rate or at the higher input rate?
The observation of
The buffer fill, like
on
yeah,
the
you
resampler?
aim basically for the half full buffer. Is that a buffer right next to the sink, so basically the sound card, or is it close to the source, so close to the RF sample rate?
The observation is only on the signals coming in and going out, whatever rate they're at.
So yeah,
This is a separate block that
Yeah.
operates by itself.
the problem I've been having, is that I get like clock jitter in a PC, so it's hard to average, like to know exactly when I've sensed that, which makes my control loop filter harder to design.
Yes. The control loop filtering is extremely difficult. The problem I see often in Windows is, you know, even if we're running like 64 sample buffers in and out, you may get one buffer in and three out, or three in and one out, and you don't know what's going to happen. And so the filtering is quite difficult. I use moving average filter and a very long moving average filter. And, you know, that's workable.
Okay, thank you.
Yeah, somewhere halfway in your presentation, you talked about the equalizer using FFT, some processing and then inverse FFT.
Yes.
And winnowing before and after the IFT. Is it possible to actually save cycles by combining the FFT for both forward and reverse FFT in one process? Or, basically save cycles by combining both forward and reverse FFT in one function call?
Well, we have to do the FFT, do the processing in between, and do the inverse. So I'm not sure I follow how we would.
Well, basically, you take an old buffer of a processed. Actually, you have the input of the IFFT. You take the late version of that and process that at the same time you do a forward FFT for the next buffer.
Yeah, I'd have to. I'm not
Okay,
sure
well,
I follow.
I'll
Maybe we
take
can
so far.
talk about it at lunch. Yeah.
Again, for the resampling ratio,
Yes.
I think that is really prohibited for digital signals requiring a definite clock, say for instance Weatherfax signals and so on. For normal voice signals it's no problem, for analog signals, but digital signals that might produce problems.
We do that all the time. So directly in response to that, like digital receivers do that all the time. Like your phone does that. It does arbitrary resampling. So it definitely works.
Yeah.
Yeah. You do need a good filter, and you do need probably more than linear interpolation if you're not overdoing it on the filter side. But yeah, it is working.
Any more questions?
More questions? So then, thank you very much for this
Okay.
very interesting talk.
Thank you.